In section 9.2, we focused on a special kind of sequence and series called an arithmetic sequence or an arithmetic series. Today, in section 9.3, we're going to look at geometric sequences and geometric series. So what does a geometric sequence look like? A sequence is geometric if the ratios of consecutive terms are the same. So with the arithmetic sequence, you were looking at differences. Now we're looking at ratios. So here you can see we have the ratio of term 2 to term 1 is equal to r. Term 3 versus 2 again is r. 4 over 3, and we have r. Now the one condition here is that r cannot equal 0. The number r is called the common ratio, and it's common because every set of consecutive terms, no matter where you pick them from in the sequence, is going, as long as they're consecutive, is going to have this ratio. So here's some examples of geometric sequences. For the first one, the nth term is 2 to the n. Let's take a look at what the ratio is of term 2 to term 1. You've got 4 divided by 2, which is 2. And just for kicks, let's see what the fourth term divided by the third term is. 16 over 8 equals 2. And indeed, our common ratio, r, in this case, is going to equal 2. Another example is with an nth term of 4 times 3 to the n power. Let's take a look at our ratio of the second to the first. So we have 36 over 12, which is going to be 3. So in this case, your common ratio r equals 3. Our last example of this type is minus 1/3 to the n. So let's take a look at the ratio of 1/9 to negative 1/3. Remember, when you divide by fractions, you multiply by the reciprocal. So 1/9 times negative 1 over 3. Oops, sorry, negative 3. Gotta do the reciprocal. 3 over 1. It's going to give us negative 3 over 9, which is negative 1/3. So r, your common difference, is negative 1/3. Okay, let's use this idea to test and see if a given sequence is geometric. So let's compute the ratio of the second to the first. So 6 over 3 equals 2. And let's try and take a look at the fourth and the third. So 24 over 12. That's also equal to 2. And if you just take a look, 6 to 12, that's multiplying by 2. 12 to 24, 24 to 48. So r is going to equal 2. And yes, this is geometric, where an is going to be 3 times 2 to the n power. And that 3 comes in because if you look at your first term, a1 is 3, a2 is 3 times 2, sorry about that. Actually, it is n minus 1. If we look here at our pattern, we have 2 to the 0, 2 to the 1, 2 squared. So you have n over here and n minus 1 over here for the exponent. Okay, let's take a look at this other sequence over here, 1, 4, 9, and 16. And let's test to see if this one's geometric. We've got 4 over 1, which equals 4, and 16 over 9, which definitely does not equal 4. So this sequence is not geometric. Sometimes you are going to want to find the nth term in a geometric sequence. And the way we go about doing that is using this formula. You can find any term in your sequence, an, by using a1 times r to the n minus 1. Let's take a look at why it's n minus 1. So a1, well, in order for this to be written as a product with this power r is going to have to be raised to the 0 power. So that's where your n minus 1 comes in, because we want a1 to be standing on its own for the first term. So a2 is going to be a2 times r. a3 times r squared. Oops, sorry, those should be ones. Your fourth term now is going to be a1 times r cubed. The fifth term, a1 times r to the fourth. And following that pattern, your nth term is a sub 1 times r to the n minus 1. So let's try and find the 15th term of the geometric sequence with a1 equal to 20 and r equal to 1.05. So we want a sub 15, we're plugging in n equal to 15. That's going to equal a1, which is 20, times r, 1.05, raised to the n minus 1 power, so 15 minus 1. And that is going to equal about 39.599. So that is the 15th term of this geometric sequence. Let's take a look at another example. This time we want the 12th term of the geometric sequence, and we're given the first 3 terms. So first let's find our ratio. And we'll do 15 over 5, which is going to be 3. And we can identify our first term. So a sub 1 is equal to 5, and r is equal to 3. N is 12. And our formula from the last slide, a sub n is equal to a1 r to the n minus 1 power. So let's plug in what we know. A12 is going to equal 5 times 3 to the n minus 1 power, which is 11. And if you put that into your calculator, you should get 735. So that is the 12th term in the geometric sequence beginning with 5, 15, and 45. Next, we're going to look at what happens when you don't know what A1 is. In this case, being that we don't know what A1 is, we can't really use AN equal to A1 r to the n minus 1 directly. But this equation is going to help us to find the 14th term of a geometric sequence where the 4th term is 125 and the 10th term is 125 divided by 64. The equation that we're going to use is going to be A10 equals A4 r to the 6th. Now, why do we use this equation? If I were to look at finding the 10th term using this equation up here, I would have A10 is equal to A1 r to the 9th. And then I would have A4 is equal to A1 times r to the 3rd. Now if I take the ratio A10 to A4, so A10 over A4, that's going to equal A1 r to the 9th over A1 r cubed. The a's are going to cancel out, the A1s, and you have the ratio A10 to A4 is equal to r to the 9 minus 3 power. Using those exponent rules, we subtract. And finally, we find r to the 6th. Now if I just multiply both sides by a to the 4th, I get this equation over here. Okay, so let's go ahead and start by using this equation, and we'll come back to this concept over here in just a minute. But first, we just need to plug in the 10th term is 125 over 64, and that's going to equal the 4th term, which is 125 times r to the 6th. Now I divide both sides by 125, and I get 1 over 64 equals r to the 6th. Taking the 6th root, I get r equals 1/2. And the way you would do the 6th root on your calculator is you would do 1 divided by 64, parenthesis, then you would do a caret and 1 divided by 6 in parentheses. So that's the 6th root on your calculator. Okay, so we know that r equals 1/2 now, and let's go back to this idea of taking the ratios of different terms and seeing that the difference in the power of r is what we want for the power. So A14 Okay, so let's set up our equations for finding A14. So A14 is equal to A1 r to the 13th, and A10 again is equal to A1 r to the 9th. And let's find the ratio of those two terms. So A14 divided by A10 is going to equal A1 r to the 13th over A1 r to the 9th. A1's cancel, and we get r to the 13 minus 9 power, which is r to the 4th. So A14 is going to equal A10 r to the 4th. We know A10 and we know r, so let's go ahead and substitute those in. A10 is 125 over 64, and r is 1/2, and we're going to raise that to the 4th power. And if you do the math, take a minute, figure it out, you do 125 over 1024, and that is your 14th term in the geometric sequence. Okay, let's do another example like that one. This time we're going to look for the 6th term, and we know the 4th, and we know the 7th. So using the idea from the last example, we know that A7 is going to equal A4 r to the 6 minus 3 power. So A4 r cubed is going to be r7. So let's go ahead and substitute in for A7 and A4, and we will calculate r cubed. A7 is 2/3, and that's going to equal negative 18 r cubed. Divide both sides by negative 18. And you're going to get negative 2 over 54 is going to equal r cubed. Now we can reduce this fraction. We get negative 1 over 27 equals r cubed. And taking the cube root of both sides, r equals negative 1/3. And be careful that you make sure you have that negative sign on your 1/3. Now that we know r, we can go back and find a to the 6th, and we're going to use a to the 6th equals, a sub 6 equals A4, and this time it's going to be r squared, because 5 minus 3 is equal to 2. So let's substitute in. A6 equals negative 18 times negative 1/3 squared. So that's going to give us A6 equals negative 18 times positive 1/9 now. And the 6th term is negative 2. Next, we're going to look at finding sums of geometric sequences. The first example we're going to look at is going to be the sum of a finite geometric sequence. So you can see here, it stops. We don't keep going on and on and on to infinity. So the sum of the sequence is going to look like, S sub n is going to equal the sum from I equals 1 to n of A1 r to the I minus 1. And what does that look like written out? That'd be A1 plus a1r plus a1r squared plus, we'll skip to the last term, a1 r to the n minus 1. And remember, in this case, r does not equal 1. Now, rather than having to calculate all this out, they found a very nice formula for us to use where all we have to know is a1, r, and n, and we can calculate this sum. So take a second to write down the formula. a1 times 1 minus r to the n power all over 1 minus r. And if you're curious as to where this relationship here came from, you can look in your book. The proof is on page 723. So when you get a chance, just take a look at that in your book and you can see where we get this formula from. Let's go ahead and do an example working with the formula. Here we've got the sum from I equals 1 to 12. Remember, we're working finite right now, of 4 times 0.3 to the I minus 1 power. If we expand this out, you'll see that your first term is 4 times 0.3 to the 0 power. Now anything to 0 is 1, so you know that this term really is just plain old 4. Plus 4 times 0.3 plus 4 times 0.3 squared plus, skip to the last term, 4 times 0.3 to the 11th power. So that's our whole sum of our geometric sequence. Now let's get the information that we need to use our formula. We need a1, which is right here. So a1 is equal to 4. We also need r, which is going to be here. So r is equal to 0.3. And we need to know n. What are we summing to? We're summing to 12. Now we've got all the pieces. So s sub 12. Okay, that's telling us that we're looking at a 12-term sum is equal to 4 times 1 minus 0.3 to the 12th power divided by 1 minus 0.3. Go ahead and put that in your calculator, and you're going to get s sub 12 is approximately 5.714. Again, be very careful when you're plugging it into your calculator. Make sure you're using your parentheses so that this all stays in the denominator and that this is all in the numerator. Okay, just like with your arithmetic sequences and series, we also have infinite geometric sequences, and the sum of this is called a geometric series. If the magnitude of r is less than 1, then the infinite geometric series is the sum a1 plus a1r plus a1r squared, on and on and on and on, all the way out to infinity. And our sum looks like s equals the sum from I equals 0 now out to infinity of a1 r to the I. So just be careful and make sure you're checking your indices of summation and you're checking the power on r, because here we've switched from 1 to n to now having 0 to infinity and I minus 1 has become I. So just keep an eye out for the differences in those formulas. One important thing to note, if r is greater than or equal to 1, so if it's not strictly less than 1, the series has no sum. So r must be less than 1 for us to have a sum. Let's go ahead and practice using the formula to find the sum of an infinite geometric series. Let's start by writing out the first couple terms of this sum. We have 4 times 0.6 to the 0 power plus 4 times 0.6 plus 4 times 0.6 squared. And it just goes on and on like that. Let's go ahead and apply our formula. A1, we can see right here, is 4. So A1 equals 4. R is going to be 0.6. And plugging into our formula, we have S is equal to 4 over 1 minus 0.6, which is equal to 4 over 0.4. And that is just 10. Notice we no longer have a subscript on our formula, and that's because of the infinity here. Okay, let's try this application problem. We're going to look at applying the concept of a geometric series to one of our compound interest problems. So you make a deposit of $50 on the first day of each month. Your savings account pays 6% and it's compounded monthly. We want to know what the balance is at the end of 2 years. Now pay close attention here to this, the first of each month. We can't just use our normal A equals P times 1 plus R over N to the NT formula, because the amount of principal is going to be changing every month, and the other thing is each $50 deposit is going to have a different amount of time to be earning interest. So what does that mean? The very first deposit is going to earn interest for 24 months. So the equation for that would be A, and I'm going to go ahead and put a subscript, a 24 on here, because this is the very first deposit we made. It spends 24 months earning interest. P is 50. 1 plus R is going to be 0.06. And it's compounded monthly, so N is going to be 12. And A24 spends 24 months, which is 2 years, so 12 times 2. So A24 is going to be 50 times 1 plus 0.06 over 12 to the 24th power. The second month, that $50 is going to earn interest for 23 months. So your new equation for the second deposit is A24 23 equals 50 times 1 plus 0.06 over 12. And now we're at 23 months. So your power is 23. Let's skip down and take a look at what the last month would look like. That deposit would spend only 1 month earning interest. So its equation, A1, is going to equal 50 times 1 plus 0.06 over 12, and it's to the first power. If we simplify what's in the parentheses, we get A1 equals 50 times 1.005. Now it just so happens that we have enough information to use our summation equation from the finite sequence, because we have a finite number of months that we're investing this money, and that equation was S sub n is equal to A1 times 1 minus r to the n all over 1 minus r. So we just need to identify, we've got A1. A1 is right here. Now we need to identify R, which is right there, because every time, if you compare 23, 24, we're going down to 1. So each time we're multiplying by R. And the number of times we're doing that is 24. So we're looking at S 24 is equal to 50 times 1.005, so that's A, times 1 minus 1.005 to the 24th power, and that's divided by 1 minus 1.005. And if you put this in your calculator, you should come out with $1,277.96. So go ahead and take a second to go back and check my math, make sure that I did it right. Here are your problems to try for next class. So go ahead and give those a shot. And great job, everybody. We will see you in class.